All right, guys, so today this would be the College Board 1.5 and 1.6 standards, and we're going to be continuing to describe quantitative data. So some of the topics we're going to cover are going to be very similar to what we did today or yesterday in class, and those are going to be frequency and relative frequency, dot plots, stem plots, histogram, and then a system that we call CSOCS. We'll talk about that more in class, but that's basically like how to describe data in an AP style way. So let's get started with frequency and relative frequency. All relative frequency does is it takes a list of numbers. A lot of times the list is a lot larger than this list is right here. So right here we have salaries, we have 39, two 34s, a 35, another 34, a 32, a 43, another 34, 185, 35, 29, and 67. And these are all salaries for the probably in tens of thousands. And what a relative frequency does is it just kind of cleans this up. So it says, okay, how many times do I see 34? Well, we see the salary of 29,000 once, the salary of 32,000 once, the salary of 34,000 four times, the salary of 35,000 two times, 39,000 happens once, 43,000 happens once, 67,000 happens once, and 185 happens once for a total of 12 salaries. Now, this already cleaned up this data set a lot, and we can already see that the most frequent salary is 34,000 at this company. But think about if you were at a mega huge company like a Google or something, or even DSST as a network, having frequencies, if you have 1,000 employees, having a frequency would make this it would clean up this data a lot more. The relative frequency essentially takes that frequency out of a portion of the total amount and it writes it as a percent. So for example, to get this 8.3%, I said, all right, I know that this frequency 1, this 29,000 is happening once out of 12 total salaries, which gives me, if I do that in my calculator, 1/12 is going to be 0.083 or 8.3%. Same thing, we do that for all of these. So you're essentially just taking that as a fraction of the total. 4 out of 12, 2 out of 12, 1 out of 12 for the rest of them. And that also allows us, that relative frequency also really easily allows us to identify where is the largest percent occurring out of a portion of the whole. So if you were to put this on any sort of graph, you would see that 34,000 is the largest amount of salaries. A lot of times we take these frequency or relative frequency graphs and we turn them into dot plots. So what a dot plot does is it takes each of those salaries and plots it where it belongs. The one thing to notice about a dot plot is that when I am plotting these, so the number 34 is going to be happening 4 times. So you're going to have a 34. 1, 2, 3, 4, 4 dots that represent 34. And what that's going to do is that's going to allow us to quickly establish, like, how skewed is this data? Is it symmetrical? Is it skewed right? Is it skewed left? The number 35 happens twice, which is why there is a 1 and a 2 happening right beside it. And this kind of gives us an idea. If you were to kind of like trace around this dot plot, this would give you an idea of the distribution of this data. The other thing that you guys should notice about this dot plot is this 185, I do not skip any numbers between 67 or 185. The reason why it's super important to not skip numbers is because we truly need to see how high of an outlier this 185 is. Every time you're labeling, remember that we need to go title, tick, tick, label, label, label. All that this does is this is going to like kind of keep you accountable, especially when you're answering FRQs, to have all the information that College Board is looking for. So we always want a title. The title here, we're good to go, is salaries at a company. We always want some sort of ticks. So that means we are showing where the count is labeling by. There's 1, 2, 3, 4. And then we always want to make sure we're labeling. Label, label, label. So we have labels on the x-axis, labels on the y-axis, and if there were any other pertinent information, we'll be including a label there. So title, tick, tick, label, label, label. We're always ensuring that all 3 of those things exist. The next type of graph that you guys see, and you guys saw this in your summer packet, are stem plots, or stem and leaf plots they might be called. Stem plots, what they do is they take the salary and frequency and they turn them into essentially like tens digits and ones digits. So for example, it kind of almost takes a range of data and it allows us to see like how many values exist in the 30s, how many values exist in the 40s, and etc. So to make a stem plot, I need to start off with my very first salary. So if my first salary happened at 50, I would start off with a stem of a 5. My first salary in this scenario happens at 29, so my first stem is going to be a 2. Notice that as I'm going through, I have a 2, 3, I have a salary in the 40s. I don't have one in the 50s, but I still need to include a 5. I don't have one from 6 to 18, but I still need to include numbers 7 through 17. The reason why, you'll see in a second, but it also has to do very much like the dot plot, has to do with those outliers and showing how much of an outlier a number truly is. So once I fill that in my leaves, or on the right-hand side of that line, I'm putting those ones place values, or in this case, it would be like your thousands versus your tens thousands, since we're talking about salary. So since 29,000 is a salary, I'm showing that 29, this key, this 2-9, would equal 29, in this case, 1,000. Now, the reason why that this is useful, same thing here, guys. We write that 34,000 4 times, so that would be like that 3-444. The reason that this is super useful is this allows us to see when we turn it on its side. Oh, sorry. We'll go over this really quick. Again, make sure you have title, tick, tick, label, label, label. Here is where that like third label kind of comes in. So we have our title. Our title would be salaries. We have our ticks, so that's what we're counting by, right? We have our X and Y values, and then we have our label, label, label. In this case, our first label is stem, our second case label is leaves, and then our third label would be that key, or to say what that represents. So not all graphs have 3 labels, but a lot of them do. Now, when I look at this graph, the reason why I cannot just skip from 6 to 18 is because when I look at this stem and leaf graph, when it skips from 6 to 18, that's not showing how big of an outlier 185 is. Right now, when I look at this, I think that like, oh, 185,000, that's like an average salary for this company, which we know is not. We know that that is a pretty big outlier. It's probably the boss or the CEO. If you leave out stems, you lose a sense of the real data. You really don't want to have these BS, this bad statistics. The other great thing, and I'm going to go back a little bit, about the stem and leaf plots is when you turn them on their sides, and we will talk about this in a second, but if you were to physically take the orientation of this graph and you were to shift it to be horizontal instead of vertical, we could kind of draw, just like we did with the dot plots, you could draw a histogram about that graph and get a really good idea of the shape of the spread of this data. Last guy is histograms. Histograms essentially take data and they group it together over a continuous track. So what I mean by that is that we are going to group these and we're not going to have breaks. So for example, my salary range, I'm going from 20 to 29, from 30 to 39, from 40 to 49, 50 to 59, 60 to 69, 180 to 189. It is important that you are not grouping this funkily, so I'm not creating a category that says 32 to 39, 43 to 67. My categories in my histogram, much like when we talked about the bad statistics between like the width of the basketball describing Kobe's accuracy or ball hoggingness, these widths all have to be the same. So my width here from 20 to 29, same width. So same range dash width. All of these have a width of 9 values, or I guess 10 if you would include the starting point. Now the group data is useful for large data sets. Just like we talked earlier, if we were looking at I mean, there's only 12 numbers here, but if we were looking at this for like every single person in DSST, then this would be really great to have. So we wouldn't have to have so many different rows. Also, this groups the frequency to make it even more compact. So we took this guy. So originally our data set, right, had 12 rows or 12 values, and we took it and condensed it into we took it and condensed it into 8 rows, and now we're taking it and condensing it even more. And the reason why this is important is because like 34,000, a lot of times people don't just have the same flat rate salary. A lot of times you'll see that there's several salaries within the range of 30 to 39. Also, salaries are continuous, so we wouldn't want to mistakenly disregard someone who had a salary of 34,554 and group them in the incorrect category. So it's just a little bit more of a consistent grouping. When we are graphing a histogram, same thing, make sure title, tick, tick, label. So we're showing the heights by drawing ticks on the y-axis. We have a title, salaries at the company, and we're labeling frequency and salaries in thousands of dollars. When I look here, it's also important to notice that this data is continuous. So on histograms, we are not jumping. We are not saying 20 to 30, and then we're jumping from 30 or 20 to 30, 30 to 40, 40 to 50, 50 to 60. We're not skipping a whole bunch, and we're not going straight to 180 to 190. All of these values have to be included here because these these x values are continuous. That means if I had a value that was, if I introduced a new salary of 33,490, I would know exactly where it fell on my graph, and I could get that plotted in very easily. Relative frequency can also be graphed on a histogram. All you do is you just change that y-axis to percentages rather than that y-axis being the frequency or number of times they're occurring. Either way works. We just have to adjust and make sure that our labels are appropriate for the graph. When we get back into class tomorrow, we're going to be talking about how we answer, and I want for you guys to write this down in your notes so we don't have to spend a ton of time with it. But CSOCS is how you're going to always answer any type of graph that says describe the distribution. C is going to stand for context, or what variable is being measured. Shape is going to talk about right, left skew, symmetric, or modes. Outliers are unusual points. So for example, in that salary range, that 185,000, that would be an outlier. It was unusual for the data. Center describes like where is your mean, median, and the general center. We talked about that yesterday. And then finally, the last thing that we'll talk about is the spread. So the spread would be like your range of values, your interquartile range, or the standard deviation. If I were going back just to kind of review here, when I look at this guy, you could easily draw. The whole point is being able to easily kind of draw and see how can I evaluate this data. Keep all of this in your brain, and we will talk about this tomorrow in class. I'll see you guys there.